Hi, hello, welcome to AMI Practical 5. This is the first time we're going to be trying this online, so this will probably be a complete train wreck, but hopefully this works out pretty decently. So I definitely recommend having the prac sheet up next to you. I will not have it up on this recording. Basically, I'll just be going through some of the basic concepts around a lot of the logic, which should be covered in the lecture, which also should be going online. This is being recorded before the lecture, so hopefully everything matches up nicely. But basically, we're going over some of the basic fundamentals that you need to have already done before doing Practical 5, and then actually jumping into Practical 5 itself. So just a quick refresher, some people in this unit may have already done units such as FCS, and I believe engineering has a unit called digital design, which they cover general logic components where you have stuff like P and Q, and if P is true and Q is true, that is the same as just true overall. But in different units, sometimes we have 0 representing false and 1 representing true. But in this unit, we'll be using just to make sure that everything is nice and abstracted, and we know exactly what we're working with. We will be working with false and true. We're not going to be dealing with stuff with zeros and ones. Though if you particularly really are comfortable with that, you theoretically can do it in a test, but I'd still recommend just up the top somewhere going 0 equals false and 1 equals true, or something like that. I believe that's the way the engineers do it, but I'm not entirely sure myself, so sorry if I've just confused people a little bit further. But, so, that no longer wants to be erased. Let me just quickly, this first one might also be a little bit of me just working out how to use the new systems. But so, first and foremost, there is, just to really jump into the bare basics, so in general we have things which are variables, so commonly we'll use P and Q, and they each can take on truth values. Oh, I don't know how to draw lines. That's a little bit nicer. And so often we represent these in tables. So the idea with this is so the variable P can be true, and say the variable Q can also be true. Actually, let me just change to a different color here. We have true, and then say we can have P be true, and just basically go through each of the different variations of this. So Q can then be false, true could be, P could be false, and Q could be true, and then they could both be false. So that's just drawing up a little truth table, which is basically for 2 different variables. P can be true or false, Q can be true or false, and then go through all the different variations of those. And then we have some basically different things we can do with them. Sorry, just practicing my artistic skills. So we have a few things. We have ORs, which is written like that. So OR, we have for and one of the other big ones we have, oh, my pen just decided to go, oh, I have no idea what just happened. Oh no! Ah! Can I get rid of that? Maybe. But so the other one we have is implies, which the computing students probably will know about, but the engineering students may not. That's just represented by an arrow. So that is for implies. Cool. So we'll go through the truth tables for these and basically go over them. Also, just specifically for the OR and the AND, if people are already comfortable with set theory, the OR is based off of union, and the AND is based off of intersect. So those are the 2 other ways of remembering those. I'll just remove those for the time being, just not to get confused though. So we can have P or Q, and so that one should be pretty easy to work out. So in this case, or simply, if this one is true or this one is true, it is true. So in the case of true and true, true or true, that evaluates to true. True or false, so P has true, Q is false, or basically takes the preference for the true, so this one is also true. Same for the false or true, P is now false, Q is true, so that's all good. And then false or false, now it can't take a true, so now this one is finally going to be false. And that's how that one works out. Cool. So, AND is pretty similar, and Q. So for this one, the idea with this is it's now both have to be the same, except it isn't. It's a little bit different still. So it's not just they have to be the same, but it's still trying to get the truth out of it. So false and false is still not true. So we have true and true. So they both need to be true for it to be true. That's true. True and false, both aren't true, so it's false. False and true, same thing, both aren't true, so it's false. And so false and false is still false because it's just asking for them both to be true. There's something which is basically they must be the same, which I can draw over here, which is bidirectional. Oh, that was a little bit terrible. Oh, still don't know how to draw a straight line. There we go. Bidirectional. There we go. So bidirectional is similar to an and, but this is where this false and false then becomes true. So I'll draw that up in a second. But so let's jump over to implies. Now implies is the one that probably people won't know about. So implies is the idea that if the first one is true, the second one should be true. So the idea is if it's the classical one, which I think was used back in some of the old computing units, if it's sunny, I will go play cricket. So playing cricket is Q, P is it is sunny. So the idea is that if it is sunny, you should go and play, be going and playing cricket. Now, so if it's not sunny, well, you can still go play cricket. I mean, it really depends. Maybe this is a much larger problem. If it's sunny, or if it's a clear weather day, that can both be valid implications. But so I'll go through and just draw it up before I get ahead of myself. So P implies Q. And grab the blue again. So true and true is true. So it's sunny, and we decided to go play cricket. That's what our statement was. So if it's sunny, and we're not playing cricket, that's where our statement says, no, if it's sunny, you should be playing cricket. P implies that Q should be true. So if P is true, Q should be true. So in this case, this statement is false. So implication basically is not a strict statement about the relationship, but it is still a logical operation. So P implies Q, this entire thing can be true or false. So in this case, P says that should be true, and it isn't, so therefore this implication is false. So what we said was that when it's sunny, we go play cricket. We kind of have a domain of when it's sunny. When we go outside that domain, when it's not sunny, what do we do? Well, don't really know. So the idea is there's a type of truth called vacuous. So basically, when P is false, when we're outside of our domain, we set it to be vacuously true. So when it's not sunny, we don't try to restrict it, is the idea. If we set it to false, we kind of deny it, whereas working with truth is always a little bit nicer. So the idea is, cool, I'm not going to say, no, you can't go play cricket. It's more saying, sure, you can go play cricket. It's a little bit funny, but so the idea is that when P is false on the imply, it will always, always, always be true. And this type of truth is called a vacuously true. Let's jump over to here. Okay. By the way, just jumping in now, so this is a just recorded part of the tutorial. There's also going to be interactive tutorials during the week as well, just heads up. So this is not the entire thing. So if you have any questions, if I go through anything pretty terribly, feel free to ask me in the following tutorials, or ask Brad or Eric, who take the Thursday and some of the postgrad ones. Cool. So let's do bidirectional. P, bidirectional. Oh, let me try that one again. There we go. To Q. So this is the one that is simply, they must be the same, regardless of truth. So and is again talking about it's trying to take both things should be true, then it's true. This one is just saying, are they the same? So it's true when they're both the same, true and false, 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 and false is true. They're the same. So P and Q is also, you can look at it as a double implication. Implication forward and an implication backwards is the idea. So it's a bidirectional implication is probably the full way of saying it. So with that, you can actually go through and start to do some fun stuff. So with this though, one of the other things that you can do with this is you can start doing some proofs. So you've got this table here, and with this table you can actually start to go through and prove that things are logically equivalent. So logical equivalency we also represent as just 3 lines. So something could be equivalent to true or equivalent to false. Something which is equivalent to true is a tautology. I believe that's how it's spelled. Let me just look it up for a second. Yeah, tautology. So if let's do, if we do say true or false, that statement's always true, so it's equivalent to true, so it's a tautology. If we have something which is true and false, that is equivalent to false. That will never ever be true. Actually, another good way of looking that up, actually, let me just write that down first. So a contradiction. Now, the tautologies and contradictions don't only just come from when you have true or false and true. You can have them pop up just through basically the way the logic's set up. So the idea with this is, so say we have something like P and not P. So that's actually another symbol I should bring up with you guys, is this before something is treated as a not. So P and not P. So this, we can basically look at that and already go, okay, cool, so this can never be true. Basically P if it's true, and not P, so if P is true, that then becomes false. True and false won't work. Put the other around, false, and then that becomes true. False and true still won't work. But one way that you can go through and prove these things is via having truth tables. So for I and got our P, got our Q. Sweet. So we do true, true, false, false, true, false, true, false. Yep, and that should be all the different ones. Oh, that looks like an E. Ah well. Okay. What's over here? So P and not P. So P is true. Actually, wait. Oh, I'm a complete fool. I didn't need Q in this. Sorry about that. Boop. It's always fun to make mistakes. P. So we have true and false. Only 2 options now. There we go. So let's jump over here. So when P is true, true, and not P, false, whole thing together. Oh, actually that's what I should go do. Completely flustered myself now. Maybe I'll go edit this out later. Who knows if I have editing capabilities or not? We will find out. P and not P. So true and false, and not P is going to be false and true, is the idea there. So that's going to be all our inputs, effectively. We're not going to have the full 4 because we're only really dealing with P. So P is going to be true, and not P will be false, so this is false. P is going to be false, T is going to, not P is going to be true, so false and true is also going to be false. So you can see here that everything here is false. So that is treated as, that's a little bit funky, I think I said that over. There we go. Alright, so false. So you can see that this gets screwed up here because everything here is all false. So this is another way of basically proving it's a contradiction. If everything in this part of the table is false, you've got yourself a contradiction. So the idea with this is you can go through and actually start to prove things are either the same if basically their truth tables are entirely matched for each of the inputs, and you can basically go through and prove that they're tautologies, contradictions, or one of them, which is the other one, is satisfiable. I believe it's spelled like that. A. So satisfiable is basically just where you have it. It is possible for it to be true. So tautologies are all satisfiable because they can be true. Contradictions aren't satisfiable because they cannot be true. And satisfiable is just it can be true. So that's the idea around those. So some of the questions you'll be running into are stuff like, is this satisfiable? Those ones are very, very nice to solve. Basically just find a single true case. Tautologies and contradictions can be a little bit harder to do because you have to go through and actually prove them in their entirety. Cool. So, jumping on into probably actually into the practical now. So some of these are a little bit fun. So first and foremost, one thing before we jump into some of the proofs is that P implies Q can sometimes be a little bit difficult to work with. So when you have ors and ands, you can do some fun stuff with them. And when you have nots, they're a lot easier to work with. So if you have a not, say, on a P and Q, that then becomes, so that's equivalent to not P or not Q. It's kind of like a multiplication that you kind of apply into it. So you apply it to the P, apply it to the Q, and that's all good. Now, same idea for not P or Q is equivalent to not P and not Q. So basically flip the or to an and. So you can kind of view it as this. So not P and Q means that either P or Q must be false. So in this case, not P, not Q is kind of saying, is Q false, is P false, and it must be one of them. So makes sense there. So not P or Q means that both P and Q must be false. So not P and not Q. Cool. And so P implies Q doesn't really fit into this not idea. So if we have our not on our P implies Q, there's not really anything we can directly do with that. So what we can do with it is, this is actually the same as not P or Q. Now that's a little bit strange just to jump into, but we'll go through and do another quick proof. So P, Q, and not P or Q, and P implies Q. Cool. And we'll get our size 4 and roll that off. Artistic, I know. Sorry. So true, 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 false, false, true, false, false. That should be all our different variations. So, not P or Q. So we can do another column if we want, just like we did up here with not P, but it's not too hard to work it out. So not P, so these two are false, these two are true. So in this case, it's false or true. So that one's okay. Now we have not P, so false or false. Okay, that one's going to be false. Now we have not P, which is true, or true, which is true. And we have not P, so true or false, which is because it's an or, still true. So that makes us happy. Now for our P implies Q, we've already done that one up here. So we can basically just copy paste that down here. And I've done the exact same order here, so it's the same idea. But so just to go over it, true implies true is our main case. We're saying that's what we want. If P is true, Q should be true. This case is P is true, but Q isn't true. So this implication is therefore false. And then when we're outside of our kind of statement idea of when P is true, Q should be true, but we don't really make a statement about if P is false. So the idea is then it becomes vacuously true. We just let everything be true. And we see, oh, those are all entirely equal. So the idea with this is that these two statements are equivalent. They are the same thing. So this is true. You can say that entire thing is equivalent to true. That's one thing you could say. So they're always the same. Oh, actually, what you would do here if you wanted to do that, actually, just as a side little note, you'd chuck your bidirectional in there. So say that they are always the same. And then if they're always the same, implies true. So you're stating that you're stating this bidirectional is true. Cool. So with this, so we've got our truth here now. So we know that P implies Q and not P or Q is the same thing. What we can do with this is when we have a not P implies Q, or again any other type of thing, what we can do first is not P or Q is what that is effectively equal to that we just worked out. So this is something which we can work with. Not on a not is basically just removed. So when we apply this to our first kind of element here, so not P, that goes back to being P. Onto our OR, we know how to work with that. Our OR is an and not Q. We just apply it directly to that one. So our not P implies Q turns into P and not Q. So if we actually wanted to see how that is actually entirely not the previous one, we can chuck it quickly in here, and the idea is this should be always the opposite of this, because it should be the not of it. So let's chuck this back in here. So P is true and not Q. So true goes to a false. So true and false, that's a false. True and false. So in this case we have true and not false, because we have a not there, so this becomes true. So then we have P, which is false, and any false on an and is immediately false. Don't need to really evaluate the rest of it. And false, same thing, but now false and false. We're going to end with false and true, but it's a true. It's a and, so it doesn't matter anyway. And so you can see here that these are entirely opposites. So again, that is kind of proven that this is the not of this, and also a not of that, because those two are the same. So hopefully that makes people feel a little bit more comfortable with this kind of idea and how you can actually start working with nots on P implies Q. And these can be really useful when you're starting to go through and start proving tautologies and stuff like that, because if you can get them down to some very basic ones, you can work out some very basic things. So if you have anything like P and not P, as we kind of stated before, that is just the same as false. It's a tautology. If we have something like P or not P, that's always going to be that's going to be a contradiction, and this will always be a tautology, because this will always be true. If P is false, the opposite one will be true, and the OR will take that and say it's true. If P is true, we'll just take that, even though the other one will be false. But with the top one, regardless of they'll never ever be both true. That is impossible. So that's why that one will not work out. So if you can basically reduce things down very, very low to just being this, you can start to get some easier stuff. So if you can reduce something to a P and not P, you can get a false, and then P or not P, you can just get a true, and then you can have statements like true or Q, and then you don't need to care about what Q is, because you have true or. So that entire thing is equivalent to true. So you just start basically doing small proofs like that. Cool. All of this proof here is actually all question 1. So we don't actually need to go over this again when we should jump into the practical. This is just also part of the bare bones fundamentals, is that these are all actually the same. These are all your fun little implications. So that's question 1 from the practical. So we're going to skip over question 1 and jump straight to question 2. So consider the following propositional statements shown below. For each statement, with the help of truth tables, determine whether the statement is satisfiable, tautology, or a contradiction. Sweet. So these all use P, Q, and just those. So first and foremost, let's P and Q. So we'll draw those up first, and we're going to need the 4 rows. Sweet. So first and foremost, we have true, 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 and false, false, and true, false, and false. Awesome. So with this now, our first one up is P implies Q. We've already gone through that. We've already shown that that can both be true and false, so therefore that one is just satisfiable. If it could only be true, then it would be a tautology. If it could only be false, it would be a contradiction. But the fact that it can be true and false proves that it is satisfiable. So satisfiable, in general, you say is it's true and can also be false. The way you can prove it is that. If you can show that it's true, that shows that it is definitely satisfiable, but it could also be a tautology. So if you want to prove that it's just satisfiable, you have to go through and actually show that it's true and false is both possible. And as soon as you have one example for both, it's purely satisfiable. So one that we didn't actually touch on was P implies not Q. So let's go through and evaluate this one. So remembering how implies works, so when this is true, this should be true. When this is true and this is false, then it's false. But if P is false at all, then it's entirely true. So that's actually a really good step to basically see if we can make the left-hand side of anything be false, then we know this is true. So first and foremost, we basically go look at basically the left-hand side, which for us is just P. Sometimes it's a lot more complicated, so sometimes you can't make the left side false. But in this case, it's just a single variable, so it most certainly can be false. So just to basically shortcut this one, we know the left-hand side can be false in a case, so we know that it will be true because of the implies. We can make the left-hand side false, therefore it can be true. But can we make this be false is the idea here. So let's try and pick a situation where it could be false. We can go do the entire thing, which is definitely useful, but doing a smarter way of this is trying to aim for what we want to prove. So let's check first and foremost always if it's satisfiable, because that's the shortest one to do. We just need two cases, one true, one false. For contradiction, we need them all to be false. For tautology, we need them all to be true. So let's see if we can aim to now get one of them to be false. So the one case where this is false is where the left-hand side is true, but the right-hand side is false. So this is true, this should also be true is the idea. So if this is true and that's not true, then it's false. So P being true, okay, cool, that'll be one of these two. And then we want to get Q to be false. So we take it when Q is true. So we have P is true, true. Q, right-hand side, we can make this false. So true, not, false. Sweet. So in this case, that one will be false. And just using those two, we can state that this is satisfiable. And I'll just do one more of these ones before jumping over to the next ones. Let's go pick ourselves a pretty fancy nice one. So let's grab the last one. P implies Q implies P. Oh, let me just undo. P. Cool. So, with this. So first and foremost again, this simply cannot be a contradiction, because on our right-hand side, we can make this false. So as soon as we've got that right-hand side there, any of our false situations makes the implication vacuously true. So all good, problem solved. So with this, we then want to see, cool, is it always going to be true? Can we make this false? So cases where this will be false, again, is where we have true up here. So true on the left-hand side, and we want the right-hand side to be false. Can the right-hand side be false? Most certainly can. So Q, when Q is true, but P is false, then that happens. But does that work out with this? So the only time that we can make this entire statement false is when P is true. So if P is true, this P over here is the same P, so it must also always be true. So this can start to get a little bit crazy. So what we can actually do is I'll just break this down to the side. So we'll still be working on this, but I'll just work over here for a second. So I'm going to come up with Q implies P. Oh, why do I keep doing that? Q implies P. Just as a little side note. And let's quickly just fully write this one out. So in this case, true to true is true. We have false to true is true, because this is a vacuously true. True to false is when this is false, and we have false to false, which is vacuously true again. So that's the truth table for this one. It's a little bit weirdly the way around just because of how we got these ones set up. So it's not the same, exact same for the P implies Q. That's because we've just got the P and Q's different ones the other way around. But so this is what we've got here. So the only time we can make this false is when P is true. We need this to be false. So these top two options here is when P is true. But when we look at this, when P is true, Q implies P is also always true. So true will then imply true, which is true. And same down here. True implies true. True implies true. Oh. So false, P is false again. Well, whenever the left-hand side of an implication is false, it's vacuously true. So this is a tautology. That is always true. You can never make that be false. And so we had to go through the entire thing to show that every single time it is always true. So that's basically how that one works out. So same kind of thing for a contradiction, which are pretty easy to go through. But those ones, unfortunately, you will have to go through everything to show that there's not a single case. Or you can actually start to go through and prove not through a truth table, which can sometimes be easier or sometimes a little bit harder. But so with implications, it can be very nice to sometimes spot the left-hand side or spot the right-hand side. Implications are very easy to target true and false conditions. Very easy to make it true just by targeting the left-hand side, making it that false. And then you've got a single situation where this entire thing can be false, which is when the left-hand side is true, right-hand side is false. Basically see if you can hit those two targets. Cool. Okay, so let us go through and do something. One other thing to actually do, I will actually state though, is if you can't make the right-hand side false, that doesn't necessarily mean that this is false overall. It just means that sometimes the left-hand side is only true. And if that's still the case, then you just have to target just this one section here. So if it limits everything, it doesn't necessarily have to fill out the entire board just to see what it comes up with. Okay. So let's keep going. So let's jump now to question 3 is going to be pretty basic. It's just going through and filling out the truth tables for a bunch of different things. So those I'll quickly go through and run through one of them because that is a good way of showing how to build up a larger set, and also has 3 variables. So let's do question 3. Actually, yeah, this was 5 and 2 from question 2. This is, let's do question 2. I'll leave some of the more other ones to you guys. So we have P, Q, oh, that was a very long Q, Q, and we'll take, oh, so we're also working with R. So they're using capital letters, I'm using lowercase, but that's okay. So in this one, we're going to have a little bit more, and I'll draw this down later. But so the idea here is we now have true, 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 false, true, false, true, true, false, false. Then that should be everything for that one. So then we have false, true, true, false, true, false, 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 true, false, false, false. Hey, that should be everything, I believe. Let's draw this down. There we go. Cool. So that went from 4 lines through 1, 2, 3, 4, 5, 6, 7, 8. Gets quite a bit more. So doing truth tables for more and more variables does start to get a little bit cumbersome, unfortunately. So if you can sometimes try to prove things not via truth tables, if you're starting to have P, Q, and R, especially if P, Q, R, and Z or something, it's going to get real big. So if you can later on start to use just some logical proofs of where you do transformations. So let's do this one. So we have an overall statement, which I'll do over here so I don't have to work backwards later on. Oop, that is a straight line. So we have P or R implies Q and, whoop, lost where I was writing, and R. Awesome. So P or R implies Q and R is what we're going to be working towards here. So now to make our lives a little bit easier, kind of like what we did up over here, but now we're planning for it, let's go through and I'll make this just two. Our first one, we're going to have P or R, and then Q and R. Whoop. Q and R. So with this, P or R, so if one of them is true, take that. So go through and just quickly evaluate that one. Cool, I believe that should just be the only ones where they're both false. Yep. Cool. And so in this case, then Q and R, so when they're both true, we have true there, and we have true here, and that should be it. Then everything else is false. Okay, so we've now kind of got our left-hand side and right-hand side. And so first and foremost again, because we've got an implication here, vacuously true is one of the easiest ones to basically target. So we see false, we know that those are both going to be true. So we know two cases where this is already true, and fill them out from there. We'll basically just check the normal implication rules. So true implies false is false, true implies true is true, and false implies anything is true. So first and foremost, we want true and true. And we'll just go through, and if we have true and false, that'll be a false. So we have true and true, that is true. True and false, that is false. True and false, nope. Because we want our left-hand side implies this, that should also be true. So that one's also false. True and true, yep, that true implies true, true does not imply false. True implies false, no. And there we go. That's the entire thing. So that's drawing the truth table for P or R implies Q and R. So it can be really nice to break this down basically into smaller steps. And just as I was talking about up here, where the left-hand side trying to aim for that to be false or aim for that to be true, sometimes it can be a little bit more difficult. And sometimes if the left-hand side is a tautology, that can change things. So you have to basically target just the true-false condition if the left-hand side is always true. But so that can sometimes be nice as well to identify if you have a tautology on the left or if you have a contradiction on the right. One really nice thing is if you can find that you have a contradiction on the left when you're trying to prove satisfiability, tautologies, or contradictions. If you have an implies with a contradiction on the left, so the left side is always false, then it's always vacuously true, therefore it's always true, therefore it's a tautology. So stuff like that. That's where we start getting into some more of the interesting, the logical transformations and fun stuff like that. Cool. So to jump to the next part, we're gonna, for question 4, we're gonna also introduce a slightly new idea, which is entailment. So entailment is the idea that it's very similar to P implies Q, very, very similar, except P implies Q is still a logical operation. Entailment is a statement of relationship. So this one is saying P, when P is true, Q should be true. Entailment is this symbol. Well, that is a terrible drawing of it. It's basically this. This says when P is true, Q is true. So this is saying it should be, this is saying that it is actual truth. So you can kind of also view it as P implies Q is always true, is one way you can actually look at it like that. But probably the better way is just saying that this is a logical operation which can be true and false, whereas this is an actual statement of truth, that this is a true statement. So when P is true, Q must be true as well, is the idea around that. So it's not saying it must be, it's saying that Q is true. It's a better way of saying that. It's an actual relationship. So the idea with this is basically going down and seeing that whenever the left-hand side is true, is the right-hand side also true? So that's how it's very similar to P implies Q, but it's just a fundamental different meaning. This is a relation, whereas this is a logical operation. So, with this, which of the following cases does the knowledge base, KB, entail the proposition S? So the knowledge base is basically some sort of rule that is known, and then the proposition S is basically the output of that. So we have something like, let's do question 1. That one's fun. Should be good enough. So let's go through and just work with our truth table. So our top one, we have P, Q, R, and S. So we have P, Q, R, and S. So we have true, 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 and you can see this is going to get, complete fool of myself. S is the proposition in this case. Getting ahead of myself. We have R again, true, and we're going to go down to our 8 again, hopefully, 1, 2, 3, 4, 5, 6, 7, we'll just have space. True, true, false, true, false, true, true, actually let me just fix that one up before I confuse myself. Oh my god, there we go. True, false, 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 true, true, false, true, false, 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 true, false, false, false. There we go. All good. And from there, this is an R, I promise. Sorry for my dodgy R's. Cool. So our knowledge base, in this case, is that P and Q implies R is our knowledge base. And our proposition, that is a wiggle. And our knowledge base, S, is that not Q and not R. That's our knowledge base there. Oh, sorry, that is our proposition. So we have our KB, our knowledge base, and we have our S, which is our proposition. Do not ask me why that is called S. Confuse me and we're going to confuse a few more. But without further ado, let's go through and start evaluating some of these. So let's just quickly go through all these, and then I'll talk about how, if it entails it or not. So P and Q. So P and Q, trues, and basically whenever they're not both true, that'll be false. And so quickly, so we know how to make that false, and we have an implies. So anywhere where they're not the same, this entire statement was going to be vacuously true. So the only times that they are the same is up there, and everywhere else it's going to be different. So that left-hand side will be false there, therefore the implication will be vacuously true. So up here, the ones we have are left-hand side being true, true and true, true and true, and then implies are, we want it to be true, and true and false is our one case where that will be false. So not Q and not R in this case, so not Q, so flip all your Q's, and not R, flip all the R's. And so in this case, we're going to go false and false. Well, that's false. Well, this already does not entail. Well, that's sad. Well, but let's quickly go through and just keep finishing this off. So the only time that this is going to be true is when they're both false, which is this spot here and this spot here. And everywhere else, any kind of combination other than true and true, which is because they're both not, so it'll be a false and false on this side, will be false. So this one does not entail. Because the idea is, when this is true, that must be true. When that is true, that must be true. When that is true, it must work like that. And you can see that that is definitely not the case in this case. There are some of them, but this relationship is not true, basically, is the way that this works. So this statement of relationship is false. Again, another way you can view this as well is treat this as a implication. So that implies, and that should be equivalent to true. So when it's false, because it's an implication, you don't really care, but whenever it's true, then it should be true is the idea. So you can treat it like, I said like this before, is equivalent to true, is another way of looking at entailment. But in general, the way you really just want to look at it is just when this is true, is that true? If so, P does entail Q. That is a true relationship. Whereas in this case, it is not the case, so it is a false relationship. This knowledge base does not entail S. So let's quickly go through and start up another one to keep going through one that does do that. So let's just go to the next one. So keep working on question 4. So let's just do question 4.2. So in this case we have P or Q and not R. So all of that, actually that one's bracketed like that, and not P. That is our KB, our knowledge base, and S, our proposition, is that P implies R. Cool, simple enough. So let's once again go through, and so we have P, Q, and R. I just made that very difficult for myself. So we're going to have true, false, false. We've got true, actually, let's not do that. Let's do true, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, and false, false, false. Cool. Just go through all the different options. And hey, that didn't work out too bad. Someone ended up bulging out at the bottom there, but it was okay. Okay. So let's quickly go through and once again make this a little bit nicer for us. This one is a little bit bigger. Let's grab P or Q. Then let's grab P or Q and not R. And then we'll evaluate the entire knowledge base, which will then be P or Q and not R. Yes, that one. And not P. And then our proposition is just P implies R. Cool. All good. So with this, let's start going through and evaluating. Just making sure that was, yep, that's all right. So P or Q, so basically in this case, where either one of them is true, so to say not the false cases. So the only times they're both false is in those two there. So it's false there, false there. Otherwise, every other spot is going to be true. All good. Yep. And so in this case, so P or Q from over here. So let's just fix that one up. P or Q and not R. So not R over here is going to be just the inverse of that. So this and the inverse of that. So, but it's an and. So the idea here is that when this is true and this is false, because it's a not, then it'll be true, but otherwise it will be just false. So if you're looking for a true and a false here, so true and false be true there, true and false, true, true and false. That one's a true, and then everything else will be false. Cool. Then we have P or Q and not R, so that's all good, and not P. So that's our one here, so we're just building on that, just adding in the and not P. So all of these, so basically again we're looking here for true and false, because we're doing not P. So where it's true and false, so true, true and true, true and false. Here's the one case where that is true. True and false. True and false there. Everywhere else is unfortunately true and true, true and true. So everything else is going to unfortunately end up being false. Actually, that looks like a true there. We can fix it up. False. Yep, just making sure. Because we've got this, so we want true on this side and then false on that side, so yeah, that is the only one. Huh, so sad. And so P implies R. Over here, I can already guarantee that this actually won't also entail. So P implies R when P is false, so this entire bottom section here will be true. So those bottom four. So P implies R, those are all true, and immediately we can see that this isn't going to entail. So P implies R when R is true over here, some points. And so basically when P is true and R is true, we're good. So true and true, true and true. But we have true and false, that's where that implication becomes false. So over here, actually, I'm a fool. Sorry. Because this actually does entail. This one does. Because this was our knowledge base and that was our proposition. I got a little bit confused for a second. So the whole idea here is that when this knowledge base is true, this proposition must also be true. It is true. This is only true in one situation, so it actually makes it very nice. So we only have to check one. Is it true here? Well, yes, it is. And we don't need to care about any of these other ones, because we only really care about when this is true, is the idea. So, hip hip hooray. Awesome, we actually did have one that does entail. Sorry about saying that wasn't going to be entailed. So again, the way you can look at this is because you have the P implies Q is equivalent to true. When it's false on this side, you know that it becomes vacuously true, so it's always true. So the only case we need to look at is the other case of where we're not being vacuously true. So when we have a true here, we need true on the right-hand side. So, sweet. Our KB does entail the proposition. So you can write out that full one there. That does. It does entail. So that is very nice. Wonderful. Cool. So let's set up a new one again. And so, which of the following statements for question 5 are logically equivalent? Question 5. Let's just jump into question 1. So with this, question 1, we have not P and not Q. And, the word and, so not P, and Q. Let's do the lowercase. Sweet. So the idea here is it's saying, are these logically equivalent? So, are they the same? With this, basically what we want to go through is we can go through and do the truth table. That's totally fine. But so one thing I'll quickly show you guys is that you still can put this through and just do transformations as we've talked about before. So we have our not P and not Q, and we're basically asking, is it the same over here? So first things first, we can just put that not in there. We have not P, and we're doing the not on the and, which makes it into an or, and not Q. And we can immediately see that that is not the case. We have not P and not Q is not the same as not P or not Q. So we don't actually need to go through and draw up the massive truth table, which would be a lot more work. We can just immediately see that that is not the case, because these two are not the same. Problem solved. So you can go through and do the truth table, but sometimes think about working with this sometimes. So 2. So over here we have, it's basically the exact same thing. Not P or not Q is equivalent to not P or Q, and once again put the not in there, you get not P and not Q, so therefore nope, we have not P or not Q, and we have not P and not Q, so that one doesn't work out. Before we jump on to question 3, there's 2 things that we really probably need to go over, and there are some fun little rules that you can work with. So the idea with this is that there are some rules. So when we start going to our fancy proofs, we can have, so we have what I call our distributive laws. And those revolve around the idea that, so if we have, say, P and Q or R, that is the same as, equivalent to, P and Q or P and R is the idea with that. And we also have the same idea for the or, basically variation. So P or Q and R is equivalent to P or Q. Oh, that one went crazy. P or R. So those are the same. So we also have what we call absorption rules. Absorption. I thought it was a B there, it was actually a P. So absorption rules, which are the rules that P and P or Q is the same as P, is the idea there. Same idea with if you have P or P and Q. Those are the same. They're both just the same as P. So these ones really let you kind of cut down on stuff. And the way you can kind of look at that is the idea that, well, with this, if you look at P, so actually probably first one easier to do is P or. So we have P or P and Q. So if P is true, well then this is always going to be true. And if P is false, well then that's also actually going to be false because we have the false on the and there. So if P is false, we rely on the and because this won't be taking the true from the or. And then false inside here, this and doesn't matter what Q is, will also be false. P and P or Q is going to be the exact same thing there. So P and P or Q is equivalent to P. Now that's actually what question 3 is actually getting us to go through and prove. It's asking if P, so question 3 is asking if P is equivalent to P or Q and P. So Q and P can just be written as it's equivalent to P or P and Q, which is the same thing as this absorption law here. So if you want to go through and draw the truth table for that, feel free to go and do that. But so it's also a nice way to kind of just think about it in your head. So in this case we have, is this going to be the same as P? So we have P and Q. So if P is true here, it's and, so we rely on this second part. So true and P or Q. So if P is already true on the or, is just going to be P. So P will basically take hold of this being true. So if true and true. If it's false, then it's simply going to be false, regardless of what Q is. So those are the same there. But so you can actually go do the truth table for that if you guys like. Our question 5 also then goes through our other one and goes through another proof of P implies Q being the same as, oh actually that is not the same. Cool, let's quickly jump into that one then, just as the last little thing to do. P implies Q. Is that equivalent to not Q implies not P? So once again we can go through and truth table this, or we can jump in and start to do some fun little tests. So to make this probably look a little bit nicer, removing implications sometimes makes proofs a little bit nicer, but so what we're going to do here is we're going to go convert those both into the alternate forms of the implications. So if you'll remember, P implies Q is equivalent to, too many strokes, not P or Q is the idea. So same thing with this, so then not on this one, so the Q there then becomes not Q, so that becomes standard Q, the implies becomes or, and we leave the second term, so it stays not P. And with that, an or you can kind of move around, we have not P or Q. Hey, those are logically equivalent. Awesome. So just general stuff like that. So you can actually go through and actually start to prove things with that kind of general idea, which works out pretty nicely. Cool. So for the last one, we'll go through and quickly touch on just some from question 6. My Q's are getting bigger and bigger with every single question we go through. So let's quickly do, yep, 1 is a nice one. So P or not P. Again, I recommend going through and doing these with truth tables, but the idea with this is the, I said before at the very start, is the classic true. If P is true and not P is false, then if P is true, not P is false, then the or you still take the true, and if P is false, then not P is true. So it's all good. But for the proof of this, you would still go through and do P as our single term, and then we have, let's also do not P, and then we're going to have P or not P. Sorry. So we have true, false, which is false and true, and in this case, they're both true. And that would be our proof for that. So then we'd say tautology. So that is all good. But so let's quickly just do one more of these. Again, these doing proofs for satisfiability contradictions and whatnot. Try and aim for true cases, false cases. But when trying to prove for a full tautology, if you can prove a single false case, you're done. So instead of doing the full truth table, sometimes go for that. If you're trying to, again, prove something is a contradiction, and that's the only thing you're asking about, find a single truth case, you're done. And then if you're doing, but if you want to prove that it's entirely a contradiction, you'll have to go through and do the full proof. If you try and do it's entirely a tautology, you'll have to do the same thing as well. So with this, let's quickly just do P bidirectional. Bidirectional. So is the same as equality. Another good way of looking at it is not P implies Q and not Q. Okay, bit more of a beefy one. So with this is probably a little bit hard to just approach on your own, just from inside your head, but it's probably not too bad again. So the idea with this is doing a quick check. So we have P on the left. So we need both of these to be equal. So we're going to have true or false on the left, and we have a P over on this side with an implication. So we know that we can make this true when this P over here is false in this case, or the not P, so we need P to be true here. So when P is true here, this entire thing is true, because that's when that left-hand side becomes false. So when P is true, this entire thing is true, and yep, if P is true, that'll be the same there. So if when P is false, well, okay, rather than keep talking about it, let's actually start getting into the proof. Because then if in that case, we're gonna have to start going into more in-depth parts. So we have P, we're gonna have Q, let's have Q and not Q. And for those who remember what I've talked about before, that's going to be an important part. So not P implies Q and not Q. So now I haven't directly mentioned it yet, but for those who remembered, good job. But I'll get to it in a second. So we're going to have true, true, false, false, true, false, false. I can give myself extra room. So now, the next one I came up with was Q and not Q. That's a contradiction. That's what I was trying to remember. So remember, we had a few basic ones that I drew up in the first one. We have P and not P is always going to be false, and P or not P is always going to be true. So with that, this is one of those cases where we actually have that in there. And if you can identify it, it can be a little bit nicer. So we actually know this is already going to be false. There's nothing that can satisfy Q and not Q, because we're going to have true and false, false and true, and any single thing like that. So in this case, our right-hand side is always false. So the one case where this could be false then is that the single case is where this is true and that is false. So this is always false, so can not P be true? Well, it most certainly can be. So not P can be true when P is false. So these two down here. So not P is false, so that makes this true. True implies always false, doesn't work out. So in those two cases, that one's false, and when P is true, it becomes flipped because it's not P, so it's vacuously true there. So that is our right-hand side. Now, is this the same as P, is what we're looking for? And true, 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 false, false, false. Hey, it is. This is a tautology. So this is a tautology because these are all the same. And because our final one, it's a tautology because they are equal, and our logical operation here is, are they equal? And if they're always equal, well then, it's always true. It's a tautology. I'll draw it in green. Yay. Awesome. But yeah, so when going through these, it's very, very easy to just basically, for this is proving tautologies, find a simple contradiction, find a contradiction to the rule, find one false case, and you're all good. Otherwise, you will need to go through and solve for all. But so that basically, I'll probably wrap this up here. I'll leave some for the basically interactive practicals we'll be having throughout the week. Hopefully this was okay. Please give me any feedback. This is the first time I've ever done any sort of digital online stuff like this. I probably rambled quite a bit. If this is also not the best means of doing this, or anyone has any other better ideas, feel free to also bring those up. I'm just going to quickly go over all the other ones, so if people need to see them anymore. So we've got all those. Again, I'll draw this one, which is the same, almost same as bidirectional, saying equivalent to equivalent. But yeah, so hopefully that went pretty good, and I'll see everyone, or everyone who isn't in the Thursday Pracs or X Pracs, throughout the rest of the week. Cool, thank you very much.